For today's talk, I'd like to welcome Dr. Naeem Abbasi, who is joining us to talk about carbon accounting and modeling for climate solutions, a demonstration of enabling technologies. Dr. Abbasi is a research scientist at Agriculture and Agri-Food Canada. He specializes in agricultural greenhouse gas modeling using biophysical models and machine learning. Dr. Abbasi has developed enabling technologies, including the EPIC user interface, DNDC model calibrator, and Teal climate carbon accounting platform. He completed his PhD at McGill University. His work bridges field research with digital innovation to advance climate solutions in agriculture and corporate sectors. Please help me in welcoming Dr. Abbasi.
Okay, thank you for the kind introduction. So I'll jump right into the presentation. Looking at the time, I'll try to be in time or a little bit earlier to leave more room for more question answers. All right, so today the topic of the presentation is carbon accounting and modeling for climate solutions. And I will demonstrate some of the technology that I've been developing all in all last 10 years or so. Here is the outline of the presentation. First, I'm going to explain what is climate change. I'm sure everybody knows about it, but I'd still love to explain emissions from soils, which is my core expertise. I will explain some of the field studies we have done and what we found out of them. Then machine learning models that we created ran actually on the data and how that turned out. Then the biophysical modeling that I'm currently doing. I will show some results from there. There are some model enabling technologies. Like when I started doing biophysical modeling, I realized there was a lot of bugs, so to speak, in modeling, and they are not very user-friendly. So I wanted to solve some of those problems. While I was doing the work, I was also solving my problem and creating technologies that can solve problems for other modelers as well. Then I'm going to zoom out a little bit. There's a part of agriculture and greenhouse gas emissions. And there's a part about my presentation is corporate greenhouse gas emissions. I think it would be beneficial to a lot of you guys, because if you're taking a career path in kind of corporate sector, that part of the presentation would be more relevant, where I'll be introducing what is GHG protocol, what are different scopes of emissions, and then I will show you automated carbon accounting platform. And then we'll close with a little food for thought kind of end of that presentation. So I'll go right ahead. Next one is climate change. What is climate change? So I like to give the example. Imagine there are two blocks. One is made of metal and one is made of wood. And you put them both in the sun. After 20 minutes, you touch the wooden one, it will be not as hot. But if you touch the metal one, it will be hot. So that's the property of materials of conducting and storing electricity. These are different materials. They may have same volume, but they have different properties to conduct heat. In the similar way as there are gases in the periodic table, all different gases have also different conducting capacities. So carbon dioxide in general is considered to be that kind of metal that stores a lot of heat. So imagine we have a lot of carbon dioxide in the atmosphere. We have a lot of that quantity that holds a lot of heat from the sun, essentially. So that is essentially climate change. When we are putting more and more carbon in our atmosphere, they behave like this metal in the atmosphere and cause global warming. Next, today I'm going to talk about emissions from two different sectors, not comprehensively, but I will touch base on some of them. One is agriculture, two is corporate sector. So let's just jump right into the first one, that is agriculture. So the problem is that nitrous oxide is a big problem. It's a big greenhouse gas. It is more potent than it's 265 times more potent than CO2 emissions. And our soils are deficient of nitrogen. So the most applied fertilizer is nitrogen in our agriculture sector. and we need to reduce N₂O emissions that are caused by this nitrogen. So there is a bit of a knowledge gap, and that we know how to make those BMPs that can reduce these emissions essentially. So first, we did a field study. We got 4 new shiny plots of land, and we tested 2 fertilizer management practices and 2 water management practices. And these were kind of designed in a 2x2 design. So this is one plot. This is how it looks like. We added synthetic fertilizer and we added tile drainage, which is regular tile drainage. And then here, this is controlled tile drainage. Controlled tile drainage is slightly different, where we control the water table at a certain height. In our case, we controlled it at 46 centimeters depth, and regular tile drainage was at 85 centimeters depth, where the pipes are laid for tile irrigation systems. Here, this is solid cattle manure. Solid cattle manure was applied as a primary fertilizer, but then we also applied some synthetic fertilizer as well, just to make sure that the N supply is same. Primary is coming from solid cattle manure, and whatever we can't bring from cattle manure, we supplemented it with synthetic fertilizer, and that made an apple-to-apple kind of comparison. The study lasted for 4 years. I took samples every year, every summer, essentially, in the field. This is just a quick image of how dimensionally it looks like, each plot. Jumping right in, these are the results from that study. So we found out that cattle manure reduced N₂O emissions by 25%, but increased CO₂ emissions by 30%. Water management, the effect was that controlled drainage reduced N₂O emission by 37%, but increased CO₂ emissions by 2%, which is not a lot. And then overall, because when we are applying some BMPs, if we are going all in and applying both like innovative ideas of solid cattle manure and controlled drainage, in that case, we will see a 56% reduction in N₂O emissions and 33% increase in CO₂ emissions. As I mentioned, N₂O is 256 times more potent than CO₂. So increase of CO₂ would have regardless happened, because it was a cattle manure that was a catalyst for it, essentially. And it will emit in any ways, and no matter which way you dispose it, it will emit that. So N₂O emission reduction is essentially a good gain to have. But that's not the end of the story. We have to figure out if it affects our yields, because that's the bottom line. So we took a whole bunch of samples from soil, from water, from plant, and we processed them in the lab. These are all the parameters we processed and figured out, which includes, soil, organic matter, carbon, nitrogen. Then in the plant, we have how much nitrogen is taken up in the grain, in the biomass, etc. And here are the results. So basically, you're seeing a pattern here in terms of organic matter. These fields have been treated with cattle manure for a very long time. So with that, you see that fertilizer has an impact. In all years, you see that impact is there. That's because cattle manure increases the overall organic matter in the soil, which means it improves the soil health. Soil health, very important. The next part was that to understand that the uptake is not significant. That was a good thing, that we didn't have any impact on grain yield, no impact on crop biomass. That means we didn't have any losses or any side effects per se from a farmer's bottom line perspective. So that's a good thing. Here is the yield. It was corn-soybean rotation. Here corn is less just because it was planted too late. Otherwise, the yield would have been same. But across different plots, you see yield was not affected by these practices, which is a great thing because you're reducing N₂O emissions by 25%, 50%, but not reducing the yield. And that's the best kind of BMPs out there. Okay, so quickly, just reiterating the same findings, long-term application of cattle manure improves soil health, fertilizer water management do not affect nitrogen uptake. That means they do not impact yield, which is great. And integrating soil and plant and uptake parameters have shown that improving nitrogen recovery is actually better. And then it, of course, reduces GHG emissions, which is what we talked about. So, okay, jumping next. So we had all this data, we find all these findings. Let's try to model it. How can we model it to see if our climate factors or field factors can explain emissions? So tomorrow, if we don't have the observed data, we can still predict it. And that's where modeling is essential. So we used 6 machine learning models, which are here on the screen. 3 are classical regression type of, 3 are shallow machine learning. I didn't use any deep learning models because at that time the compute power was not there yet. So for the machine learning models, we took data that could be easily available for different fields. So we had data for soil moisture, temperature, organic matter, but more importantly, we had the climate data like precipitation, temperature, maximum, minimum, radiation, evaporation. So we put that all data in with our observed data that we already had, and we applied a k-fold approach. It's essentially a technique where you want to make sure that your machine learning model is robust. So the way you run a machine learning model is you provide it with observed data where it learns, and then you give it data that it has never seen before, and it predicts. And if it can predict well, that means the model works. But first time when you do it, it could be a fluke. So you want to change that testing data again and again to make sure that you get similar results, to make sure that the model is working. So here in first iteration, we had 2012 kept in our pocket. We gave it the rest and let it run. It gave us good numbers. Then we kept 2013 in the pocket and gave it the rest. And that's how we did a 4-fold approach with it. Here are the results on one nice screen. So we compared 6 models. One of them was going to be the best, which was the random forest case. It's never always going to be the case. Point we are making is they are still good, robust models to use in this use case. This was probably the first paper published on the application of machine learning and GHG emissions from agricultural soil at that time. So you can see from this spider graph, you can see the green round is most widespread. That means it has the best performance. You could get as good of a performance as 0.86. And that was pretty good, because the scale is from 0 to 1 essentially. So that's the conclusion of research. So quickly, findings that they are effective, they are efficient. It took very little time to run them. It took a lot of time to set up them, but took very little time to run them. And they do work better than mechanistic models. And I'm going to show the mechanistic models very soon, shortly. One, they perform better, but there are still uncertainties in the sense that they are still black box models. There are no equations that you can explain. There are weights and biases that you can take out and use them in the future, but they have to be done they have to be tested in terms of temporal and geographical variations, essentially. Random forest was the best. It already is explained. So next, what I did is biophysical modeling. So biophysical modeling, and the parameter I'm working with right now is net ecosystem exchange. It's nothing different. It's CO2 essentially. So agriculture soils take a lot of CO2 in and they put a lot of CO2 out. Previous research was only on the factors that's what is getting out. In this one, we have equipment that can actually understand how much is also getting in terms of like sequestration, so to speak. So BMP's benefit and management reference practices is still the goal. So this is kind of an image, conceptual image. It's not reality, but in a conceptual world that if we apply 1 and 2 and 3 best management practices, we could be net source of CO2 to net sink of CO2. And even if we are net sink of CO2, there isn't much limit there. We can be more sink because there are all other sectors emitting. If agriculture can help one draw its own emission footprint down and then draw other footprints down, and then that way they can participate in carbon markets. They create or generate carbon credits, which can be sold in the market. In case there are production losses, they can still recoup their costs from there. So this is probably close to home. So I have 2 sites, Carberry and South Tobacco Creek, STC. These are the 2 sites, and that's where my equipment are installed. The data has been collected for the last 10 or so years. And this is that equipment. It's a very innovative equipment. It's called eddy covariance tower, and it can be used for multiple measurements. We are more interested in NEE measurements, which is again net ecosystem exchange of CO2. And they have been, as I said, been there for over 10 years now, and I have the data from these fields. So I'm using this data to do modeling with 2 biophysical models. One is EPIC, second is DNDC, Canadian version. DNDC model is well known. EPIC has also been out there for 35 years. Canadian version has been out there about over a decade now. And there has been a lot of work done on DNDC model from Canadian team to improve it for Canadian climates. So with that, what I showed you the inputs of the machine learning models. In this case, we need a bit more data, or more specific data, because there are equations. Equations require specific inputs to be able to generate specific outputs. So it's a combination of multiple empirical equations, so to speak, in a web format in a sense. So we need weather data, precipitation, soil temperature, all that. We already used it for machine learning, so we have it. Scheduling, what is the planting date? What is the harvest date? How much fertilizer was applied? What kind of fertilizer was applied? There can be slow release, high release. If irrigation was applied, how much irrigation was applied? What type of crop and species or genetics was there in terms of crop? So we put all that information in the models and the results. So this is how NEE looks like between observed and modeled. So you can see they kind of follow the trends. This is basically each year, and when you have this dotted line, means the next year. And these are only showing it for growing seasons, not the full season. And S means soybean, SW means spring wheat, C means canola. So it shows you what crop was cultivated, and you can kind of see trends. These 2 are from DNDC, the bottom ones, and the top ones are from EPIC. And you can see EPIC overestimates the sequestration. DNDC underestimates the sequestration. But overall, if you're looking at a metrics standpoint, you will see that we have better metrics from DNDC. So it's 0.868 here, which has been the best model that has performed in our case. It's not 0.82, but it's not far from it either. And there are advantages and disadvantages to both techniques. Here in STC, we used cattle manure, and here it was conventional fertilizer. So in STC, we don't see that kind of performance as we see in the conventional systems because these models are calibrated for conventional crops, essentially. So if we can fully understand from a modeling standpoint that how much sequestration is going to happen, then we can essentially use this in our advantage to take the same model. It did perform 0.68 R square and RMSE of 22 kilogram per hectare per year. That's pretty small in terms of a hectare area. So it's a good RMSE. If we take that model and now we give it assumed information about what crops we are going to plant for next 30 years. And then there are circular climate models which provide you weather information of how our weather will look like for next, say, 50 years. And we can get that information from IPCC and different other providers. So and that is high resolution information at daily time scale. So we can take that information, run in the model again, and see how does it perform in the future? How would our food production would be like? Because it gives you the information about yield, which I'm not showing here because I have a ground to cover. But we'll be able to see how yield will be affected. We will be able to see how NEE will be affected. We'll also be able to see what would be the overall soil health. So this is just to reiterate that confirmation that DNDC performed well. You see orange is DNDC and the further white is spread, that means its performance is better. And here it's about soil temperature. So you're seeing soil temperature performance. Soil temperature is kind of similar with both. In this case, no, but they are not far from each other except one metric, which is MBE, which could be a bias introduced in the winter time. Yield, clear winner, DNDC, ET, almost clear winner, ET case. And then NEE, as I showed you, works quite well with DNDC compared to EPIC. Okay, so now we're jumping on to the enabling technologies. So when I started the biophysical modeling, there were issues. One, EPIC, when I installed it, it was a folder and it had a lot of TXT files. No information, TXT files. And in those text files, there are numbers. You don't know what those numbers are, and you have to figure out. So there's a manual where you have to count line number this, field number this. This is about the year of the years of the yield simulation. Okay, so I go and change it. So what I did is I created a user interface, which was not there before. So this is a screenshot of the user interface. And to be sure that we will be showing it, I can narrate it probably. I'm not even in the folder. Okay. So there is an audio on the video, but it's pretty self-explanatory, and I'm going to narrate it. That once you run it, this is how the user interface looks like. This is how your folder looks like when you install it. And these are all TXT files. You could see the file, there was no understanding of how to use it. But you can go in, you can read TXT files through this user interface. You can make changes. What that means is written here. So you just open it, you can make all the changes, you update it. TXT files at the back will be updated on their own. Now you can see that is updated, and you can run the model right from there. Just click the button and you can run the model. We haven't gotten into like output. Output is still complicated to fetch and pull, but I created my kind of handy dandy Excel tools for it to complete my work. But that's something that can be done in the future. So that's one technology that I was able to put together that will help future modelers. The second one, going back to my presentation, the second one was calibration. So in the modeling, there is a issue of calibration. When you are modeling, it gives you some numbers, and models are not always perfect. You have to calibrate them for a specific site. So for example, if there are like PHU, which is basically accumulated heat unit in a crop, and there can be a range for that. We don't have a hard and fast number for it. We can calculate that number, but the model might not work with that number. So you can kind of have a wiggle room that, for example, 1200 to 1600 can be a good PHU. So you can calibrate the model to make it actually work for you. But then 1200 to 1600 is a lot of numbers, and you have to run it again and again. You have to fetch that output again and again. You have to compare it with observed information and see, did I do okay? No, maybe I should try another number. So for that, I created an automated system that just does it. It has the way to run your iterations on your terms, essentially. So this is the user interface of that DNDC calibrator looks like. I have it open here. I can probably run it from here. Okay, no, wrong screen. Right screen, yeah. Okay, so this is that model I was talking about. You can take it any target output information parameter like yield, soil temperature, etc., etc. I'm just going with simple yield, and a modeler, DNDC modeler will know what I'm doing, but these are basically, there are a couple of pages of instructions on how to use it, but it's pretty self-explanatory in that sense. If a modeler is using it, they will know what we need to do. So I'm just giving it the information about observed yield from the field that we already have. And then it will find its yield from the model on its own. And I'm going to give it parameters in terms of like, make it run like a list of parameters. So I don't have to just give it PHU, I can give it a list of parameters. It runs based on Bayesian technique with a Gaussian process as a surrogate model. So it essentially expects what would be the next RMSE. So it really makes efficient choices when which number to pick, like 1200 to 1600. It starts with 12, 16, then figures out where should I go up, should I go down. That is where Bayesian technique comes in play. I can put any number of iterations here. I have run up to 15 iterations. As the number of iterations increases, the last few iterations are pretty slow to run, but 100, 200 iterations run at a normal pace. I'm just going to hit it at 10 for now and just make it run. And it will show you what it is doing here. It will show you what numbers it has taken in this present iteration, and then keep running all along. Once it's complete, it takes a bit of time. So once it's complete, it compiles an Excel sheet, and in that Excel sheet, it shows you with each iteration what numbers it used, what was the modeled yield that came out of it, which one was the best one, and then it gives you a graph between the modeled and observed, a nice bar graph it gives you to see visually how close you could get. So here it's picking all these parameters, it's deciding a value. You can see RMSE is 431, which is actually quite low when it comes to yield. R square is 0.85, which is very solid. And then it will just keep doing it again and again until it gets better and better. I wanted to show the results. Maybe I can, if I try. I will do that. Okay. This is a sample example file to show how those results look like. So these are different parameters that it was calibrating for. These are the different values it has selected for each iteration. This was run for 200 iterations. And this is the best iteration where RMSE is 903 and R-square value is 0.65. And then this is a data comparison that I was talking about. It picks the best, shows you how it performed, and you can also have the data from all iterations or 200 iterations. So you can sort of analyze what was happening within the model, what was affecting it more or less. So it can be more analytical in that sense. Okay. Let's say close, come back. Okay. So these are the two enabling technologies that I've created recently. Going back. So that's a bit of a wrap up on agriculture side of things. As I mentioned already, the next step we are going to take is actually understand how would it be affected by the climate change. So we'll have the future scenarios, we'll run those, and we'll see how it looks like. Sustainability of agriculture essentially hinges on all these that we are doing. And I'll explain that later a little bit. But what we need to keep doing is observe, model, report, repeat, because that's the way to sustainable agriculture, sustainable health of our well-being, of the food security that we need to secure, essentially. Let's jump to corporate sector. So I have done a bit of work in the past in the corporate sector, consulting companies, etc. And in the corporate sector, the Bible is GHG protocol. GHG protocol has different protocols out there. And the most important one is here, this is called the corporate protocol, which explains how emissions should be categorized and calculated. And more important now is happening is that companies are trying to report their carbon emissions. And also the regulators are trying to push more towards the companies that they should report their carbon emissions. And then you have heard about carbon tax that we were supposed to have with this government, which we haven't got yet, and I don't think we're going to get it anymore. But this is the technology that will be behind it to actually understand what is their carbon footprint so that their carbon tax can be calculated. So there are three scopes. These are basically considered boundaries, operational boundaries, according to corporate protocol. So there are three scopes: scope 1, scope 2, scope 3. Scope 1 is direct emissions, which means fuel used in the cars, fuel in the generators, etc. Anything that your company did, burnt fuel directly, that is scope 1. Scope 2 is indirect emissions, but only from purchased electricity and heat and steam. So if your company is using electricity, it has been produced somewhere else. So the emissions happened where that thermal plant was, or nuclear plant was, or hydro plant was. Emissions didn't happen on your premises. So these will be considered as scope 2 emissions, and they are exclusively for electricity and heat and steam. Scope 3 emissions are all other indirect emissions that happen from your business. So that are divided into two big ones, that like upstream and downstream, and then there are 7 in upstream, 8 in downstream, or vice versa. Basically, you took a flight for business travel. From that one seat of plane travel that you did, it doesn't come in scope 1, it doesn't come in scope 2, it comes in scope 3. Somebody else burnt the fuel on your behalf. Somebody else did an activity on your behalf or your business's behalf, essentially. So those are all the categories that includes business travel, waste generated, capital goods purchase, you buy furniture, you invest in things, etc., etc. Okay. So for this one, we used to do in consulting companies is we used to create Excel models where we would have emission factors, we have activities, we have data, we just create Excel-based models. And as a consulting company, we had a turnover of a company comes in, gives us the data. We take about 3 weeks to put that Excel together, and then we deliver the project. It was quite costly. It was highly time consuming, required a lot of skills to do it. So we said, let's create an automatic system. Unfortunately, we are not the first one who did it. There are a lot of companies out there. There are over 200 carbon accounting platforms. We are probably the best, and I could be biased about it. But so we have a system where there is a huge database of emission factors, and it's sector agnostic. That means even a church or a government office or city municipality can do their carbon accounting and understand what is the carbon footprint of their organization. That also includes agricultural companies, just not in the operational, like deep in the operational sense, more like like fuel burnt in the tractors, etc. kind of stuff. So this is the dashboard. That's how the dashboard looks like. Probably we have a video to show on this. Yeah. So this is, by the way, available online. If somebody wants to use it, they can try it. steelclimate.com. It's free to use. You just say start trial version and you can use it, essentially. It has all the bells and whistles in it. This is, again, you're seeing scope 1, 2, 3, category-wise, scope 3. There are 15 categories. They're all there. And that's how the dashboard essentially looks like. Once the business comes in, they can hit, add a business unit. They can put in any business unit where that business unit is, and they can just say add. So you have that business unit in now. Like McDonald's, they have a lot of outlets so that they can put all the information there. Those are business units essentially. They can go scope 1 fuel. What kind of fuel? Click, click, click. What kind of quantity you used? 900, and there you see the data is right there. And if you scroll, you will see the carbon emissions there from that particular activity. You can have thousands and hundreds of thousands of activities. It can just handle it. And then if you have data in Excel, it can just take the data from Excel and calculate it for you. It can also generate a nice PDF report for your company, like a comprehensive report of what your emissions looks like. And then if you have done carbon accounting with the platform once, next year it will be easier because you can just transfer your last year's data and then punch in the information for the new year. You can edit everything, delete everything. It's quite feature rich. There is also a carbon bot there because everybody talks about AI, so we have to AIfy it. So there's like all kinds of questions you can ask about carbon accounting. And the AI that we have is basically fed with all the information that is related to carbon accounting only. So it's a RAG kind of model, and it runs locally on our computer. So yeah, that is that technology that is now out there. People can use it. Companies can use it. Yeah. Okay. So next one is just understanding that how does this actually help? Like we're doing a lot of accounting, we're doing a lot of modeling, we're doing a lot of field work. How does it actually help? The way it helps is essentially, I'm using an analogy here where when you're driving a car and you pay attention to your left a little bit, you will see your steering kind of tilts a little bit on the left. It's an auto response that is given by human nature. Wherever we focus, it kind of goes there. So if we are observing, if we understand it, if we model it, then our entire action system will be geared towards reducing it. And that will be an automatic action. We don't have to do huge extra efforts or create huge decarbonization projects. They do help, but observation, modeling helps better, because what can happen effortlessly, unconsciously, is far better for humanity. It requires less brain power. It just happens. That kind of relates to that quantum physics effect of observer effect, where particles can be behaving as particles or waves, depending on what is your expectation from it. So our expectation is that we want to be net zero, and that's what we are expecting it to happen. We just have to keep observing, modeling, and accounting for these things. So I'm going to stop here. I think that's my time. Here are my contacts. If anybody wants to talk about anything related to these technologies, I'll be happy to chat. But I will open the floor for question and answer.
Thank you for the really great talk. And now, questions.
Thanks for the really neat talk. So I'm curious about your use of like machine learning, like random forest versus this mechanistic model. So you seem to, if I understood correctly, the models like random forest actually outperform the mechanistic models.
Yes, that.
And the random forest are, at least in my experience, much easier to use. So should we be switching? Like, should we get rid of these mechanistic models and just go for these kind of more, I guess, predictive models? Or just like I said, there's not a lot of mechanics behind it, but they do work, right? I'm just curious what your perspective is.
That's a good question. So there's a saying among modelers, one me being a newbie in it, but all models are wrong, some are useful. And it's a very famous saying I've heard so many times. That's the reality of modeling, is that all models are wrong. They have something that is wrong with them. Like machine learning model, first, we have to have a lot of data to give it for that it's trained. Biophysical models, we don't need data. We just have weather data, just slap it in and we'll give you something to work with. Machine learning models, that means you need to have a lot of observed information to be able to train it and run it. Not that biophysical models are any perfect, but they have certain benefits of their own. All in all, I would encourage all the technologies to kind of push forward, keep working on them, because when I speak about, like, people talk about like renewable resources, and they say solar is going to fix climate change, and then wind is going to fix the climate change, and then there's like wave technology, tidal waves, like that's going to fix the climate change. They all together will fix the climate change. So we have to kind of keep everything moving forward in that sense.
Thank you.
Sure.
I had a question. I was just wondering, were there any major limitations that you came across when you were building the models?
They're all wrong, basically. That's the biggest limitation they have. But the information is we're trying to understand it, what is going to happen in the future. If we can sound some kind of alarms with these models, we will change the behaviors. So solid cattle manure that is already out there will be thrown in some ditches somewhere where it will make a lot of environmental issues. That could be used as fertilizer. Win-win. Environment wins, farmer wins, cost is reduced, etc. And we don't have enough, cattle manure in the world to replace all this, synthetic fertilizer. But at least we will be able to tell the farmer, you're going to reduce your emissions by 25%. And that number is a very strong and powerful indication of what he's gaining out of it. And if he's, creating some kind of carbon credits out of it, he should. So the limitations, an infinite to count, but they are very useful when it comes to their utility, essentially.
I have a question, just curious. So just so I understand correctly, you helped generate the teal climate automated system. Do you know how many, first of all, when did you do this? And do you know how many users you have using that system right now?
Excellent question. I started that initiative about 3 years ago. It was finished about a year and a half ago, and it has been live since. And I have been busy with different other modelings, but there is a team behind it that keeps it up to date because emission factors do change every year. So that team does the work. I'm not a developer. They do all the development stuff on it. And right now, there's one consulting company who does carbon accounting for people in Excel. So they have found a way to just use our platform, cut their time, and they are still providing their final user as an Excel sheet, but backend they are using our system to do the carbon accounting. So they are quite happy. They find a lot of bugs. They give it to the team. Team always fixes those, and then they want to automate a few things, which the company has done. There are about 6-7 people behind it who work every day hard to keep it up. It's like a tax consultant, for example. You give your tax consultant, something, you file your taxes. They don't do it in Excel. They subscribe to, TurboTax or some bulk kind of license they buy, and they serve all their clients, and they submit it through that as well. It's same thing. You want to do carbon accounting, and anybody can be a carbon accounting consultant now because there are tools behind them that they can use to generate everything, download everything, put their own touch to it, confirm everything is good, and then give it to the client with confidence. It doesn't eliminate human altogether. What it does is it reduces the human stress, less chances of error, more checks and balances in place to make sure nobody is giving you I took X flight from Montreal to Toronto and my emissions are 10 tons. I wasn't the only one in the plane. So you need kind of a system for it. So I hope that answers the question.
Thank you very much. Very interesting.
Hopefully I didn't miss this. Definitely outside of my area of expertise. So, you're working in landscapes in Manitoba, like Canadian prairie landscapes. Is this got broad applicability across all sorts of different sort of agricultural types, throughout the world? Or do you think there's any limitations that, where there's unique things in the prairies that might be driving things?
Well, that's a very interesting question. And the way agriculturists describe soil is different on every inch. So the differences are just there. They exist. From a general standpoint, we understand the temperatures are different, the humidities are different. General area is different. The landscape is, I know Manitoba flat area is small, but it exists. And that flat area is mostly the bread and butter for the province. I was actually there in September. Yeah, I wasn't there in August. So I was fortunate to see the entire landscape. And so, yes, there are differences. So DNDC works very well in eastern part of the Canada, where we have, Ottawa, Windsor, big hubs of agriculture, basically. It works well. It doesn't work as well in terms of Manitoba because it's not calibrated for that area. And that's where these limitations also, one of those limitations I can highlight is that they're not especially one. They need to be reacting to the location. So there should be an input in the model that takes in your latitude and longitude and tweaks its equation a little bit to make sure that it's addressing Manitoba climate. Major issue was soil temperature when I was trying to model it, and it just thinks it's way too cold. It's cold in Manitoba, but it's not that cold as it shows in the model. So there are limitations. So certainly, yes, location matters a lot.
It is way too cold here. You're not wrong about that.
So I'm curious about your observed versus your predicted values. like you said, there's often mismatch between observed and predicted. So when you start to dig into it a little bit, do you have a sense of why you're seeing over or underestimations? Like, do you know if they're overestimating soil respiration or they're underestimating photosynthesis? Do you kind of have a sense of where or why the mismatch is occurring?
So that's a very intricate question. And yes, that's where the DNDC calibrator kind of comes in place and gives you a whole bunch of like an Excel sheet. So you can just plot it. What was my RMSE for the last 200 iterations against what was my PHU like? And you will see a graph. So you will understand what is that yield being driven by? Is it driven by PHU? Is it driven by irrigation? Or is it driven by soil, porosity, hydraulic conductivity? So you can kind of analyze all that with that big tool. And before this, there was nothing like that before. So this essentially does help not only to calibrate, but kind of dig deeper into like understanding the personality of the model, the behavior of the model, and like what are the quirks in it. Okay, yeah, if PSU hits this, then there is no change. And if soil what field capacity hits this, then everything goes out of whack. You get wrong numbers or flatlining, etc. So you can kind of understand the personality of the model through those calibration models because it just gives you a whole bunch of data.
I think I like the term like model personality.
Yeah.
I think I can.
Oh, come on. Yeah. It's a whack-a-mole. You're trying to calibrate it for yield and then your NE goes off. You're trying to fix the NE and your yield goes off. So good luck.
Anyone else? No? Okay. Well, thank you again, Dr. Abbasi, for joining us.